Now let's investigate in more detail the isothermal process that was mentioned in the previous section. This is a thermal process that occurs at constant temperature, and we will do this by considering the isothermal expansion or compression of an ideal gas. Consider, for instance, a metal cylinder that consists of n moles of an ideal gas placed in a large mass of hot water at a constant Kelvin temperature T. The cylinder's piston is initially held in place, so the initial volume of the cylinder is V initial. The gas does work on the piston and moves it upward. This occurs as the external force applied to the top of the piston is reduced quasi-statically. The pressure in the gas decreases as the volume expands to its final value, V final. Here is the pressure versus volume graph for this process. The solid red line in the graph is known as an isotherm, which means at constant temperature. The work done by the gas is not given by P times delta V, since P is not constant during the expansion. Nevertheless, we can use integral calculus to show that the work done by the gas is still equal to the area under the curve. Here is the result. The work done is equal to the product of N, R, and T times the natural log of the ratio of the final to initial volumes. An important question to ask is, where does the energy to do this work come from? The internal energy of any ideal gas is directly proportional to its temperature. For example, U is equal to 3/2 nRT for a monatomic ideal gas. Therefore, the internal energy of the gas remains constant throughout the isothermal process, and the change in internal energy is zero. As a result, the first law of thermodynamics becomes the following. In other words, Q is equal to W, and the energy for the work comes from the heat in the hot water. The system has removed heat from its environmental surroundings to do work on the piston. Likewise, if the piston were isothermally compressed, the equation above to calculate the work still applies, and heat will flow out of the gas back into its surroundings. Now let's consider the expansion or compression of an ideal gas that occurs adiabatically. Recall that this means there is no exchange of heat between the system and its environment. The following figure shows an arrangement where n moles of an ideal gas can do work adiabatically on a piston as it expands quasi-statically from an initial volume V initial to a final volume V final. Because the cylinder is now surrounded by a perfectly insulating material, no flow of heat occurs between the gas and its surroundings. Therefore, Q is equal to 0 joules, and the change in internal energy of the gas, as given by the first law of thermodynamics, becomes delta U is equal to minus W. Since the internal energy of an ideal monatomic gas is directly proportional to temperature, as given by equation 14.7, it follows that the Kelvin temperature of the gas must change from its initial value T initial to its final value T final. With this substitution, the relation delta U equals minus W becomes the following, which allows one to calculate the work during an adiabatic expansion or compression of a monoatomic ideal gas. When an ideal gas expands adiabatically, it does positive work on the system, so W in the above expression is positive. This means that T final must be less than T initial, and the gas cools. The internal energy of the gas decreases to provide the necessary energy to do the work during the expansion. The following figure shows a plot of the pressure versus volume curve for an adiabatic process. The adiabatic curve, shown in red, intersects the isotherms, shown in blue, at the higher initial temperature and then again at the lower final temperature. Again, the shaded region under the curve represents the work done. The reverse of an adiabatic expansion is an adiabatic compression, in which W is negative. Now our expression to calculate the work shows that T final must be greater than T initial, or in other words, the gas heats up. The energy provided by the external agent doing the work on the gas goes into increasing its internal energy. By using integral calculus one more time, we can find a relationship between the initial pressure N volume and final pressure N volume of the adiabatic process shown in the previous figure. The result is the following for the adiabatic expansion or compression of an ideal gas. The exponent, gamma, is the ratio of the specific heat capacities at constant pressure and volume. It should be noted that this relationship is consistent with the ideal gas law, as each point, PV, on the adiabatic curve satisfies the following relation, PV is equal to nRT. The following table summarizes the work done in the 4 types of thermal processes we have considered. For each process, it also shows how the first law of thermodynamics depends on the work and other variables.